We spend a lot of time discussing motion, how to express it, and how to predict it. Here, we'll switch gears into looking at the cause of these changes in an object's motion. We've mentioned in passing that any sort of acceleration or change in velocity is caused by some kind of force. So, how would you define a force? Well, remember, science is all about being able to describe and explain the world around us. So we need a definition for force that is unequivocal, no matter our setting. And so we define force, F, to be a push or a pull. And since direction of the force applied would directly influence the direction of an object's acceleration, we define force as a vector quantity. Let's make sense of forces as a vector quantity. Let's say you have a big Indiana Jones-sized boulder rolling towards you. If you somehow had the strength to stop or slow this boulder down, how would you push on it? Right, you would push against the boulder in the direction opposite its motion. By applying a force opposite to the direction of velocity, we're causing the boulder to accelerate in the direction opposite to the direction of velocity. That is why acceleration and velocity vectors must be in opposite directions if an object is slowing down. Likewise, if you wanted to speed this boulder up, you'd push with the boulder in the direction of its motion. By applying a force in the same direction as its velocity, we're causing an acceleration in the same direction as its velocity. And that is why acceleration and velocity vectors must be in the same direction if an object is gaining speed. Now, don't forget, acceleration exists whenever there's a change in velocity. And velocity changes anytime an object gains speed, loses speed, or changes direction. So, how would you push or pull on this boulder to change its direction? You'd have to push this boulder in a direction perpendicular to the direction of velocity. Don't worry, we'll talk more about this sort of acceleration in the near future. For now, let's focus on gaining and losing speed as a result of a force applied parallel to the object's direction of motion. By the way, it's important to clarify that forces don't keep objects moving. Forces cause objects to change motion. Let me take you back to an example from our projectile motion video. If a monkey throws a banana in space, that monkey pushes the banana, causing the banana to accelerate. But as soon as the monkey stops pushing, the banana stops accelerating. And if no other force acts on the banana, we know it'll just keep going at constant velocity. This is an example of Newton's first law. It can be written in so many different ways, but most commonly put, it states, objects at rest stay at rest, and objects in motion stay in constant velocity motion unless acted upon by a net external force. Now we call this a law because we haven't come across any experimental data to disprove the statement. So really, that begs us to wonder why. Why is this statement true? Why wouldn't, other than the fact that it'd just be weird, an object spontaneously change its motion? Well, the best way we can explain it is to say that there's some intrinsic property that all objects have to resist changes in its motion. That is why a net external force is required to cause an acceleration. This property that all objects seem to have to resist changes in its motion is what we call inertia. And inertia depends on an object's mass. That makes sense, right? I mean, which is more challenging to change its motion, a truck or a leaf? A gust of wind will have enough force to accelerate a leaf, but not a truck, because a truck has more mass and therefore more inertia and therefore more resistance to changes in its motion. Okay, So inertia explains why Newton's first law happens. But what is meant by the term net external force? Net refers to a sum. So if two people are pushing on a teddy bear, the bear would only accelerate if the total force does not add up to 0. We would describe these forces as unbalanced. Don't forget, forces are vector quantities. So if these two people push and pull with the same magnitude of force in opposite directions, the net force would be 0 or balanced, and effectively the bear would not accelerate. External means that an object that is not the bear itself must apply this force to cause any sort of acceleration. There you have it. Newton's first law tells us that in order to cause an acceleration, some kind of net, unbalanced, external, outside, force, a push or a pull, must be applied because objects have mass and therefore have inertia, a resistance to changes in its motion. So, what kind of forces exist? We've classified all of the pushes and pulls we know of into 4, what we call fundamental forces. We call them fundamental because all other forces we know come from these 4. So let's take a look at the 4 fundamental forces ranked in order from weakest to strongest. The gravitational force already known to you is the attraction between two masses and is also the weakest force in the universe. The weak force is responsible for nuclear decay. The electromagnetic force is responsible for the attraction and repulsion between charged particles and magnets. And finally, the strong interaction is responsible for holding quarks together in the form of protons and neutrons, and as a byproduct of that interaction, also manages to hold protons together in a nucleus. As the name suggests, this strong force is the strongest force we've discovered. Though science is a changing field, and there's a lot left to be discovered in our universe. It is theorized that when the universe, at least the universe we're familiar with, was born, these 4 fundamental forces existed as one unified force. And it was the cooling and expansion of our universe from the infinitesimally dense singularity that caused the branching of this unified force into the 4 that we study today. The 2 that will be most relevant to our studies here will be the gravitational force and the electromagnetic force. There's so much to discuss about these 2 forces that we're going to need to split them into 2 videos. So let's first take a look at the gravitational force. Okay, we've already seen the gravitational force at work. It's the force that pulls objects towards the Earth. Well, at least that's what our experiences of it are. Reality is that the gravitational force is a force of attraction between any 2 objects based on their mass and their distances from center to center. Yes, that means there's a gravitational force of attraction between you and your couch. Or wait, is that something else? Well, the good news is the couch is also attracted to you. The gravitational force is a mutual force that both objects experience. So, if this force is attracting all things with mass together, why isn't everything in one big pile all the time? Why did the Big Bang happen? Why is our universe still expanding? Well, remember, the force of gravity is the weakest of the fundamental forces. Comparatively speaking, it's about 10 to the 36th power times weaker than the other 3 forces. Now you might be wondering, why is it so weak? Well, join the club. It's so distinct from the other 3 forces, not only for its ability to extend across the entire universe, distort space-time, or attract and never repel, but also for its strength, rather lack of, leading to some very interesting ideas about extra dimensions. And it's this complexity and peculiarity of gravity that makes it a huge obstacle for scientists in their quest for a unifying theory. Mind-boggling, huh? I agree. So for now, let's address the basics. The force of gravity, F sub g, is a force of mutual attraction between two masses. We tend to quantify the strength of this attraction by measuring the gravitational field around Earth. Okay, think of a soccer field as a space where you play soccer. Similar to that, you can think of the gravitational field around an object, such as Earth, as a space where the force of gravity happens. Well, technically, the space where the force of gravity happens is actually infinite, as the universe is infinite. It just gets significantly weaker than it already is, as the distance grows. So let's focus more on the field that's near the surface of the Earth. The strength of that gravitational field, we'll call it G, measures 9.80665 meters per second per second. Look familiar? Yeah, it's the same as what we use for acceleration. That's because we measure the strength of the gravitational field around an object by how quickly an object in that field accelerates. But wait, we are near the Earth's surface. Why aren't we accelerating downwards? Well, we would be if it weren't for the electromagnetic force. We'll get to that soon. Regardless of whether or not we're accelerating towards the Earth, we're still being pulled towards the center of the Earth. And that pull is known as the force of gravity. And it's actually what we measure as weight. Here exists a very important distinction between weight, a measure of the force of gravity, and mass, a measure of the amount of matter. Weight is dependent upon your location in a gravitational field. Mass is dependent upon the stuff an object is made of, regardless of your location. Weight is measured using a scale, while mass is measured using a balance. Because they are different, they distinctly have different units. You're most familiar with the use of pounds, not the British currency, but more so, if you weigh yourself on a scale, you'd report to your weight in pounds. In physics, we tend to use a different unit of measurement for weight. We use something called the Newton. You might have heard of Sir Isaac Newton. Now, we don't just use a different form of measurement to make science more complicated. There is a reason for the use of the Newton. Remember, in physics, we're learning how some quantities are derived from other quantities. And choosing a standard set of units is not just convenient, but necessary for mathematical calculations. The Newton is derived from the standard units of kilograms, meters, and seconds. And it's a measurement that we can use for all forces, not just the gravitational force or weight. Okay. So the weight, like all forces, is measured in newtons, N. Mass, on the other hand, is measured in the unit of grams. In physics, we often use kilograms, which is just a variant of grams, because we tend to work with larger objects and we'd rather say something has a mass of 1 kilogram than 1,000 grams. Great. So that was a lot of stuff, and that was just one force. Let's recap it real quick. The force of gravity, F sub g, also known as weight, is a force of mutual attraction between two masses. It depends on the amount of mass and distance between the two masses' centers. And like any force, it's measured in the standard unit of newtons. We've barely begun to understand all the forces we experience in our daily lives. In our next video, we'll continue learning about forces, focusing now on the electromagnetic force. See you soon on Penguin Physics.